This talk is going to be based on a paper that is forthcoming in the BJPS. And if you're interested in the topic and want to read all of the excruciating details, you can download the paper at the displayed links. So to begin, I'd like to motivate the problem in rough terms and set the scene before delving into the details. So let's consider the phase space of two classical particles. The state of this system is represented by the phase point R1, P1, R2, P2, where R1 is the position, P1 is the momentum, and we have the first and the second particles there. And displayed in the figure, we have a possible state of this system, where one particle is moving left and the other particle is moving right. Now, what we should notice about this situation is that they apparently represent the very same physical state of affairs, and yet they can be represented by two distinct points in phase space. So in effect, if the particles are identical, you just change which particle has which position and which momentum by permuting the 1, -1 and the 2, 1 pairs to get S prime. And they apparently represent the same thing. Now, this overrepresentation, if it is so, becomes an issue in statistical mechanics, where we're concerned with probability measures over the phase space. And if we're asking how likely it is for the system to be in a particular state, then we can see that this might become an issue, because when the phase space overrepresents, then the probability measure overcounts. In this particular case, it's going to overcount by a factor of 2, or more precisely 2 factorial. So for every physical state, one particle moving left and another particle moving right, we have 2 points in phase space representing it. And you get the 2 factorial by permuting the 1, -1 and the 2, 1 pairs amongst each other to get a different phase point. So this is the problem. And I'm also going to motivate what I'm going to defend as my solution. And again, in rough terms, before moving on to the details. To illustrate my point, I'm just going to step away from classical mechanics for a moment, just to consider this very simple motivational example. So we have a system which flips a red coin and a green coin, and each coin can add heads or tails. And suppose that an observer who is gathering frequencies about the system is colorblind, and then they cannot tell the difference between red and green. Now, the set of physical states is represented by this space M, and we can see that it has 4 points, representing the case where we have green and red at both heads, green and red both tails, and then green tails, red heads, green heads, red tails. But for the colorblind observer, the set of observable states is given by this set omega. And of course, if you can't tell the difference between red and green, all you're going to observe is heads, 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 tails, and tails, tails. Now, what I want us to learn from this simple example is the following. When we observe a physical system, we're gathering, or in particular, maybe a stochastic physical system, we're gathering relative frequencies of elements in the sample space. So this colorblind observer is going to count how many times they see heads, 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 tails, 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 etc. And their frequencies and probability distribution is going to be based on that. Probability measures are defined on sample spaces, such that the measure of the sample space is 1. The probability measure of the sample space is 1. And if you buy into this motivational example, sample spaces are going to be constrained by what is observable. So if we step into statistical mechanics, what we're going to end up emphasizing is that the space which carries a probability measure is not going to be the phase space, but we should interpret it as a sample space constrained by observables. And this distinction is going to become going to make it more precise, and it's going to be really crucial as I develop these ideas. So now we're going to delve into the details. I'm going to state as precisely as I can the problem in classical Hamiltonian mechanics using those mathematical tools. And I'm going to describe two prominent responses to this overrepresentation, overcounting problem by Dennis Deeks and Simon Saunders. I'm going to illustrate my responses to those and then move on to my position, which is based on a new definition of indistinguishability in terms of classical observables. And then I'm going to show how this allows us to calculate and derive this overcounting factor. On to some formalism. So this is Hamiltonian mechanics. I'm going to characterize a Hamiltonian system by this triple. N is a manifold, it represents the phase space. Omega is the symplectic form, and H is the Hamiltonian function. Dynamical trajectories for this Hamiltonian system are the integral curves of the vector field capital H generated by the little h Hamiltonian via the symplectic form thus. And it will also be useful for us to introduce the phase flow, which is this one parameter group associated with the vector field capital H. Roughly speaking, the phase flow, if you take all of the integral curves together, this is the phase flow, and it tells you after a certain amount of time, t, little t, which represents the time where the system is going to be some units of time along the integral curve. And just to ground this in more familiar notation, equation 1, if you give m global coordinates where q1 are the canonical coordinates and p are the canonical momenta, then it takes the familiar form of Hamilton's equations. Given global coordinates thus, this is the physics of a physical system with little n degrees of freedom. The problem arises, our problem, specific problem arises where we apply this general framework to the physical system of capital N particles. And Gibbs states, when Gibbs wrote this famous textbook, 1902, on statistical mechanics, and he engaged with this particular problem we're concerned with today. And he stated the problem like this. If two phases differ only in that certain entirely similar particles have changed places with one another, are they to be regarded as identical or different phases? This question in the literature has been debated extensively. I think it's widely regarded as fairly cryptic, and it's kind of difficult to really precisely understand what question Gibbs is asking here. So I'm going to deploy the formalism of Hamiltonian mechanics to try and state this question as precisely as we can. For the system of n particles, points in the manifold take this form. So the position, we have 6 coordinates for particle 1, and six coordinates for each particle, the x, y, and z positions in the x, y, and z momenta. More briefly, let's represent them like this. I'd like to draw some attention to the structure of this phase point, which is going to help understand the language I'm going to be using. So let's think of this phase point as consisting of n slots into which we put single particle states. So in the first slot, we're putting the single particle state RP1, and so on. Now, we need to discuss permutations. So we're going to define this family of transformations pi ij, which are defined so that they swap the single particle states among the slots in the phase point. So pi 1n has just taken rp1 and put it in the n slot, and taken rpn and put it in the first slot. Effectively, these permutations change which particle has which position momentum. And I'd like to make some comments about how these permutations are talked about and interpreted. Sometimes these permutations are interpreted as permutation of particle labels. And sometimes they're talked of as permuting the particles among the states. I don't think a huge amount hangs on how we interpret these permutations, since what is really relevant is their formal structure. But in the language I'm going to be using, I'm not going to talk about them like this, because I think the clearest way to understand these permutations is as a permutation of single particle states over particles. My reason for this is that I'm interpreting each slot in this representation of the phase point as a particle, and the numbers, the pairs of numbers Rp, which are being permuted among these slots, are the single particle states of those particles. So this is how I'm going to talk about these permutations. They're going to be permuting single particle states over the slots, i.e. over the particles. Okay, good. So this apparatus which we've developed, I think, is sufficient now to be able to state Gibbs's problem and the problem we're concerned with more precisely. Take point S in M, and now take the point pi ij S, where the single particle states have been permuted among the slots I, J. Both of them are points in M. Question, are they in some sense equivalent? Does it, in other words, does it kind of matter which particle has which single particle state? Gibbs gives an answer to his own question, which I think is equally cryptic. And thus, if the particles are regarded as indistinguishable, it seems in accordance with the spirit of the statistical method to regard the phases as identical. And this has raised and continues to raise, I think, a whole host of questions about what exactly Gibbs meant. What does indistinguishable mean here? And what is the spirit of the statistical method? And when in his question, when he said entirely similar particles, what does that mean? What sense of equivalence are we talking about here? I am going to give mathematically precise answers to all these questions. But first, I'm going to consider two prominent responses to this question. I'm going to consider Dennis Deaks's answer first. So in a 2013 paper, Dennis Deaks essentially argues that classical particles can be named and distinguished by their different histories. A process in which two classical particles of the same kind are interchanged can therefore certainly produce a different microstate. Here's a pictorial representation of what is meant here. So let's consider an initial state. We've got two particles in a box. There's the initial state where the black particle is going up, the white particle is going down. And the argument goes, well, we could have it so that either they end up in the same position and momentum configuration, but now the white particle has taken the position of the black particle. In effect, what's happened is the dynamics has been such that they've swapped over. Or they could have just not swapped over and just bounced off the walls and come back in the same configuration. Now, if these, I've represented these particles as black and white just to emphasize the swap. But of course, in the background here, these particles are regarded as identical. And so the thought goes, well, these two final states, which are permuted versions of each other, by the way, are distinguished. Why? By virtue of the different histories that they've had from the initial state. In one case, they've swapped, in the other, they haven't. Therefore, they can be distinguished. My response to this is to point out that the case in which the system's particles do not swap must have a different dynamics to the system when the particles do swap. They must do. In one case, they've swapped, and the other, they haven't. This is because of the different dynamics. So more formally, let's just represent it as the fact that they have different phase flows. Phase flow for non-swapping, where the point S after a certain amount of time is mapped to S, and if the dynamics for swapping, S is mapped to the permuted version of S. So in our formalism, what's happening here is that the phase flow is generated by the corresponding Hamiltonian, the dynamics for swapping and the dynamics for not swapping. And so what we've said here is that the point S in this dynamical system with the non-swapping Hamiltonian is different from the permuted state in the dynamical system with the swapping Hamiltonian. And this is true, but it is not really the question that we set out to answer. What we want to know is whether S and pi1, 2S in the very same dynamical system, Hamiltonian system, are equivalent or not. Here, the equivalence they're clearly not equivalent because they're members of completely different Hamiltonian systems. So that concludes my response to this position. The second prominent response I want to illustrate is given by Simon Saunders and goes kind of in the opposite direction, claiming that classical particles are indistinguishable. And the argument, which I think is fairly widely adopted, goes like this. So suppose the particles are identical, understood to mean that they share all intrinsic properties such as charge, mass, and spin. Then the state and its permuted version represent one and the same physical state, one and the same physical situation. Therefore, the manifold is overrepresenting the physical states. There's representational redundancy in this phase space. So let's remove it. Remove the representational redundancy by passing to the reduced space, which is the quotient of M under the action of the permutation group. So the way we can understand this is that points in M prime, the reduced space, are understood as equivalence classes containing n factorial elements related to S in M by the permutations in the group. This has the corresponding effect if we've reduced the space, and so the argument goes on, well, if we've got a measure on that space, then we reduce the measure and we correct the overcounting problem by dividing by n factorial. And this, so the argument goes, solves the overcounting problem. My response to this is going to hinge on shifting gears in a way. I'm going to, instead of focusing on the question of whether these states are identical or really representing the same physical state of affairs, what we should talk about instead when we're doing statistical mechanics is whether they are actually observationally indistinguishable. So we're moving from identity to indistinguishability. So far, these are only roughly defined, but I will give a precise definition of what I mean soon. Similarly, we should stop talking about particles' properties and instead talk about observables. So this shift is going, the essence of this shift is my response to this line of argument. And I'm going to develop this in the rest of the presentation. I'm going to, towards the end, will become clear how this is in particular so different. So here's the first major bit of philosophy here. I'm going to introduce my definition of observational indistinguishability. So classical observables are represented by, well, they are functions from the manifold into the reals. Those are called classical observables. On the basis of this, we make the following definition. States S and S prime in M are observationally indistinguishable with respect to a set of observables Fi, if and only if the two states take the same value for all the observables in the set. Some comments on this. First comment, this is a definition schema. So it depends on what set of observables you choose to put in this set. For each set of smooth functions Fi you want to put in this set, you're going to get a different definition of observational indistinguishability. I'm going to use this precise notion to construct a sample space from the state space M. And essentially the point is going to be, with respect to a certain set of observables, some points in M are going to be observationally indistinguishable. We're going to identify all of them into one point, and that's going to be become a point in the sample space. such that all points in the sample space contain all and only the observationally distinct points. This shift has an effect on how we should think about quotienting. So quotienting was a key part of the Saunders response here in removing the representational redundancy. Now, typically construed, the goal of quotienting is to construct a space which is not representationally redundant, i.e. contains all and only the physically distinct states. Now, delving into this a little further, what we're really doing here is reducing with respect to a particular equivalence relation. The equivalence relation we're reducing quotienting with respect to here is physically equivalent to. Our goal in the statistical mechanics is rather different. We're not concerned with creating a space of all and only physically distinct states. In fact, as far as we are concerned, M might already do that. What we're interested in is creating a sample space containing all and only observationally distinct states. Now, if we're quotienting with the aim of creating a sample space, then what we're doing is we're quotienting with respect to a different equivalence relation than is typically assumed. The equivalence relation is observationally equivalent to. This is precisely defined as given by the definition in the previous slide. So if we quotient with respect to this equivalence relation, we do not end up with a reduced state space. We end up with a sample space. So I'm just signaling this out here that when we quotient, it's just be aware that there are other equivalence relations available. It's not just is physically equivalent to. Here we should be quotienting with respect to is observationally equivalent to when we're doing statistical mechanics. Okay. Now, let's apply what I've introduced here in a particular case. So I'm going to take my observational indistinguishability definition, and I'm going to take the particular instantiation of it where the set of smooth functions, the set of observables, is the singleton containing H, the Hamiltonian. And I'm going to call observational indistinguishability with respect to the Hamiltonian dynamical indistinguishability. So just applying the definition that I introduced, S, state S, and state pi S, where pi is an element of the permutation group, are pi dynamically indistinguishable if and only if S and pi S take the same value for the Hamiltonian. Now, intuitively, dynamical indistinguishability, this definition should entail that these 2 points, if followed along their integral curves, should be the same up to permutation. So essentially, they're the same dynamical trajectory, they're doing the same kind of thing, just differing in which particle is doing what, essentially. And in our language, this is taken to mean it should leave the Hamiltonian phase flow invariant. And indeed, you can show this, that this definition implies if they're dynamical, if 2 states are dynamically indistinguishable in this sense, the Hamiltonian phase flow is invariant. It's a proposition, it's got a proof. So it has that intuitive, nice intuitive consequence. We can extend this definition to the case where we're talking about particles. We've only so far been talking about indistinguishability of states. We can use this now to talk about the indistinguishability of particles that are represented in those states, like this. So we say 2 particles of an n-particle system represented by factor positions I and j. So these are the factor positions of the slots in my n-tuple state. Those are dynamically indistinguishable if and only if the Hamiltonian satisfies this condition there. And that is how we talk about indistinguishability of particles following on from this definition. This is so far kind of abstract, not very concrete. Just to get our feet firmly on the ground, I'm going to introduce just a couple of examples to get used to these definitions. So here are 2 candidate Hamiltonians. The first one, H1, is the free particle Hamiltonian for 2 particles. H2 is got a kinetic energy term, and it's also got an electrical potential energy term. Here, in this Hamiltonian, particles 1 and 3 are charged. They've got charge E, and this last term is representing the electrical force between them. Now, in H1, the particles are dynamically indistinguishable. Why? Because pi 1, 2 is a symmetry of that Hamiltonian. If I change which particle state has which particle, the Hamiltonian is going to take the same value for both those two states, the permuted states. And in H2, the transformation pi 1, 3 is a symmetry of this Hamiltonian. Why? Because particles 1 and 3 are both charged, and so it doesn't make a difference which one is which, in a sense. However, the transformation pi 2, 4 is not a symmetry of this Hamiltonian. Why? Oh no, that is a symmetry, sorry, as I've said. Pi 2, 4 is also a symmetry of this Hamiltonian. They're not charged, so again, it doesn't matter which one's which. But pi 2, 3 and pi 1, 4 are not symmetries. Why? Because you're permuting states among a particle that's charged and one that's not charged. So that is not a symmetry in general. So this is what I've got in the back of my mind with these definitions. Okay. With these definitions in place, I think it's now finally time that we can introduce some statistical mechanics and talk about what effect my arguments have on the probability measures that are introduced by statistical mechanics. And it will be useful in this regard just to remind ourselves how Gibbs himself introduced statistical mechanics. In his introduction, he invites us to imagine a great number of systems of the same nature, but differing in the configurations and velocities which they have at a given instant. This has come to be known as the ensemble. And what you should have in mind here, in our particular case of the n-particle system, we should imagine the n-particle system with each particle has got a slightly different position, slightly different momentum, and we've got all the possible ways the system can be, and that is the ensemble. It's all the possible ways the system can be. And Gibbs goes on to say, here we may set the problem not to follow a particular system through its succession of configurations, but to determine how the whole number of systems will be distributed among the various conceivable configurations and velocities at any required time when the distribution has been given for some one time. Here, Gibbs is pointing out, we're not concerned with the particular dynamical evolution of a system as we are in classical mechanics. We're interested in how a distribution of systems over these configurations changes with time. But this is going to turn out to be we're interested in rather the probability distribution over the configurations, and that is the main object of study in statistical mechanics. Okay, let's develop these ideas more formally. Let curly n be the number of copies of the system in the statistical ensemble. So in my language, these are going to be the number of observationally distinct ways the system can be. Now remember, I'm directly importing, putting my stamp on things here. I'm arguing that the sample space is constrained by observables. Curly n is the number of systems in the sample space. It's the number of systems in my statistical ensemble. And if that is the case, then on my interpretation, these are all and only the observationally distinct ways the system can be. Now, the number of systems in region R of phase space is given by this function, n of r. It's the integral of r of d, dp dqn, where d is the density in phase. By d, we are to think of this as the number of systems in a particular region of phase space. So if you integrate d over some region, you're going to get out some number, and that's going to tell you how many systems there are in that region. Having distributed, having taken your ensemble, you're isolating a little bit of it, counting how many there are doing a particular thing. We can define, using this, a probability measure. Mu r is the integral over r of p, and where p is defined to be d over curly n. Now, I'd like to make an observation about this particular definition in equation 9. Mu is a probability measure on m if n, little n of m, equals curly n. And you can verify this. You see, if you integrate p over the whole of the manifold to get mu m, then you integrate d over the whole of the manifold, you get nm. If nm is equal to curly m, then you're going to get mu m equals 1, i.e. mu is a probability measure over m. Now, here's the punchline. It can be the case that curly n is less than nm, because the little n function could be overcounting the number of observationally indistinguishable states. If some points in m are observationally indistinguishable from one another, this little n function is going to be overcounting them. It's going to count as distinct states which correspond to the very same point in omega. And so it is in this sense that we get the overcounting problem. This could be the case. Now, if this happens, mu of m is bigger than 1. And mu of omega, the sample space, is 1 because it's a sample space. And the probability measure over the sample space is 1. Now, if mu of m is greater than 1, well, this is not a probability measure, is it? Mu of m is not a probability measure, so we've got a problem. This is essentially the problem. However, we can always ensure that we have a probability measure on m by defining curly p as mu of r over mu of m. Now, this is harmless to define because if curly n is equal to little n of m, the measures mu and curly p are identical. However, remember our problem arose when curly n failed to be little n of m. And if that's the case, mu ceases to be a probability measure. However, curly p will still be a probability measure. Curly p is defined to be a probability measure on m because curly p of m is 1. Now, with this formalism in place, I can finally get to the second punchline, which is how to derive this overcounting factor. And there are quite a few assumptions that go into this argument, so bear with me. First, we're going to assume that we're working with the free particle Hamiltonian. Now, all n factorial elements of the permutation group are symmetries of the free particle Hamiltonian. We can then partition m into n factorial regions ui, where I runs from 1 to n factorial, which are all dynamically indistinguishable. The reason we can do this is because each point in the manifold is going to have n factorial. There are going to be n factorial points in m which are dynamically indistinguishable from one another with respect to the free particle Hamiltonian. And if we take little regions around those points, then we can say, well, we've now got n factorial regions which jointly cover m and are all disjointed as well, but jointly cover m. We also have to assume that p, as defined, capital P as defined earlier, is some function of the Hamiltonian. The importance in doing this is that p then inherits all the permutation symmetry of H. Now, any one of the UIs may be taken to be the sample space. because it contains all and only the states which are observationally distinct from each other, dynamically distinct in this case. So and given that it's a sample space thus construed, the measure on UI had better be 1. Now, since P inherits the symmetries of H, all of the mui's, the measure of UI, well, we can sum the measure of the UIs up from 1 to n factorial. This is going to give you the measure of m. And because they're all identical, because P inherits the symmetries of H, there are n factorial UIs. And since mu UI is 1, the measure of m is n factorial. And if we then substitute that into curly P, mu of m is n factorial, and so we've derived the overcounting factor. Why do we divide by n factorial in the case of the free particle Hamiltonian? Well, because some points in M are dynamically indistinguishable from one another. Now, there are some... I've packed a lot in here. This is the bare bones of this argument deriving the n factorial, and I spell out all of the details at much more length in my paper. But for the purposes of today, I just want to draw some attention to some features of this argument. In particular, just how many assumptions go into it. So if you want to derive this n factorial factor, you are assuming that we're working with the free particle Hamiltonian. Furthermore, you're assuming that P is some function of the Hamiltonian and nothing else. And those are highly non-trivial things. Your system might not have a Hamiltonian which has some other symmetries. It might be rather like the Hamiltonian with the electrical potential factor, in which case it won't have all of the symmetries of Sn. Depending on what observables you put in, depending on your definition of observational indistinguishability, your choice of FIs that go into the set of observables, depending on the symmetries of those observables, depending on which of those observables your P is a function of, you're going to derive a different overcounting factor. And I think it's interesting just to see from this point of view how many assumptions go into getting this n factorial factor out. So this concludes my main argument and all of my points. So let's just head straight for the conclusions and illustrate what I've shown you. Key to my analysis here has been the distinction between omega as the sample space and M, the state space. I see omega as being constrained by observables. And if we do this precisely in classical mechanics, where observables are represented by smooth functions, then we get a precise definition of observational indistinguishability. And following on from that, a rigorous derivation of the overcounting factor. And we've seen also what features the overcounting factor depends on. Further work, well, I think a natural question to ask, given my definition schema, well, what do you put into this set, Fi? I've shown you that if you just take that set to be a Hamiltonian, then you can get your n factorial. But I needn't have chosen just the Hamiltonian. I could have put in any number of observables. So what's going to determine which observables I choose to judge observational indistinguishability with? And finally, I feel that there are some important links with quantum theory to be made here. Because observables clearly play a central role in quantum theory. They form part of its formal structure. And I feel, and I can imagine a very analogous definition of observational indistinguishability carrying through into quantum theory like this. And one would say something like the Hamiltonian commutes with the permutation operator and some things like that. And I think it's a virtue of this analysis that I think it, in some sense, brings these two fields on a somehow closer conceptual footing in this, when talking about indistinguishable particles. And I think it would be interesting to explore that further. But I haven't, those are just thoughts at the moment. So I will finish there. Those are my concluding remarks. And thank you all very much for listening.